As you said, my name is Gabriel. I'm from the University of Vienna in Austria. And today I will talk about MobileAtlas, which is a measurement platform for mobile networks. So I'll start with a short problem statement. So let's assume you found a new vulnerability at your local carrier, and you wanted to know whether this is only a local quirk or whether this is also a problem at other mobile networks. Maybe it's a global vulnerability. I have bad news for you, because in this case, there is no suited measurement platform that you could use to evaluate whether this is the case. Of course, we have some nice measurement platforms for fixed line internet measurements. So for example, Weippl. But the thing is that for the mobile field, we have different requirements. So for example, we have a roaming status. Also, we have something like calling or messaging. Also, like on the tariff, in terms of tariffs, we have different tariffs. We have metered connections. We have zero rating offers. And therefore, we need something more specific to the mobile field. In general, mobile networks are pretty complex, so we have a ton of protocols. We have roaming, where many parties need to work together. And in general, you could say that complexity is kind of the nemesis of security, and therefore it's a very interesting research field. So if you wanted to build a new measurement platform, you basically have two options. The first approach is to use crowd-based measurements, so basically to develop a smartphone application, to get some volunteers to install that application and to run your measurements. The big advantage is that it's relatively easy to increase coverage with that approach, but the drawback is that for some types of measurements, it's just not possible. So if you wanted to do some calling experiments or maybe some expensive roaming tests, you wouldn't find any volunteers that are willing to execute tests on their phones. So therefore, we need the second approach, which is to create and deploy dedicated hardware units. So the big advantage, obviously, is that you have your own measurement environment. You can gain very accurate measurements. And, but the main drawback is that this method usually implies very high setup costs, and therefore you're kind of limited in terms of scaling. So this is the wish list for a new measurement platform. If we wanted to build a new measurement platform, we want it to be scalable, to be cost efficient, to allow very flexible roaming measurements, also to provide a very controlled measurement environment, and obviously to provide versatile capabilities. And a smartphone is not just an internet outlet, but it has other capabilities as well. We want to have the capability to do some calling experiments, and also we want to have low-level insights, so maybe even on APDU level. Yeah, when we tried to create this platform, we kind of figured that the limiting factor is SIM cards, or is the SIM card. So if you have a broad coverage, you need basically one SIM card per test unit. And also, physical SIM card switching is kind of cumbersome. So we need to find a way around that. And that's why we introduced a new approach, which is to geographically decouple and detach the SIM card from the modem. This is basically just fancy speak for tunneling the SIM card's protocol over the internet. So I'll elaborate on our approach. At first, I present the traditional approach. You just have a SIM card. You physically plug it into the SIM card slot of your modem. So both are physically connected and both are at the same location. The second approach is what we did. So we did some decoupling. The SIM card can be at a separate location than the modem. The SIM card is plugged into a SIM card reader, and then there is some relaying happening. And at the measurement device, we actually emulate the SIM card, and there is no real SIM card at the measurement probe. Yeah, and in between we have the SIM tunnel, so this is like a VPN for your SIM card or like a proxy. It's just relaying of the application protocol. Why do we do this? It's to get a nice scaling behavior. So in this example, we have 2 countries and 4 SIM cards that we want to measure. With the traditional approach, you would need to buy 2 sets of SIM cards, so 1 for each country, resulting in 8 SIM cards in total. And with our decoupled approach, we just have 1 single set of SIM cards that we can reuse at various target locations, so we just need 4 SIM cards. 8 SIM cards doesn't sound too much, but the problem is if we increase the amount of measured countries or the amount of SIM cards, this number increases rapidly. So for example, if we wanted to do measurements at 10 targets location, you would need to buy 40 SIM cards, which is a lot, especially if you need to maintain them, if you need to regularly top them up, it's not feasible anymore. So this is the overall architecture of our platform. On the right side, we have SIM providers. They allow sharing SIM cards. On the left side, we have our measurement probes. A measurement probe provides access to the local mobile networks at the target location. And with our platform, we can virtually and dynamically connect any SIM card on the right side with any measurement probe on the left side. And then we can execute measurements as if the SIM card was actually plugged into the measurement probe. The nice thing is also that the SIM card is just responsible for generating some session keys, so we will have the same performance basically as if the SIM card was actually plugged into the modem. So you could even do some speed tests and you won't see any difference. So yeah, as already said, the SIM provider is responsible to share SIM card access. It's just a piece of software you execute on your computer, and we've implemented support for various reader types. So for example, a PC-ST card reader, but also your normal Android smartphone. So there is this Bluetooth protocol. It's called SIM application profile, and it allows sharing access to your SIM card. And the nice thing is that if you have an eSIM figured as your primary SIM card, you can also use this to give access to your eSIMs. So we also support eSIMs. So the second component I want to present is the measurement probe. It's based on a Raspberry Pi 4. It's fairly low cost, so it's less than $300 per probe. And for the SIM tunneling, we simply reuse the Raspberry Pi GPIO ports, and we reuse the UART to emulate the SIM card to the modem. So this is a closer picture. We can see that we attached to the SIM slot of the modem and then simply connected this wires to our GPIO ports. So we've built this platform and we've deployed it in various target countries. Right now it's deployed in 9 European and 2 North American countries. And yeah, now I'll show you what we can do with it. So I'll present a few showcases. In the paper we've had 5 showcases, but because there is only limited time, I'll just show you 2 for now, and maybe you would read the paper if you're interested in more. So we've bought 14 SIM cards of 5 different countries, and then we've executed measurements in all available target countries. The first measurement is some privacy-related measurement. It's ringback tone fingerprinting. The ringback tone is the tone that you hear when you call somebody and when you wait for them to pick up. And the interesting thing is that this is issued by the operator that is terminating the call. So in case of roaming, it's issued by the roaming partner. And thereby you could use this tone to kind of deduce the country of the person that you just called. So there are very obvious differences between the US and the EU, for example. So on continent levels, you could even hear it with your ears that there's a different ringback tone. But also, like within Europe, for example, there are noticeable differences on a country level and even on an operator level. So even within one target country, you could tell the operator from listening to the ringback tone. I've brought us a few examples. So this is, for example, from a Romanian provider. It's the spectrum, so we see the peak frequency and also the amplitude. This Romanian provider uses 430 Hertz. If we compare it to a German provider, for example, the German provider uses a different peak frequency, and also it's louder. The German provider is louder. If we compare it to another German provider, we see that, again, 426 Hertz are used, but the signal is less loud, and also we have some noise, so some side lobes on the lower frequencies. So this is a scatter plot, and we can see that the operators are separated nicely. So you could nicely identify the operator by only taking the amplitude and the base frequency. Obviously, there are also more metrics that could be used. So for example, overtones or the duty cycle. So the last showcase I'll show today is the APDU analysis. As many of you maybe know, the SIM card is like a tiny computer. It can run code. It can also issue some commands. So there's this proactive SIM command instruction set, and it can take over control and tell the smartphone what to do. And since we have full insight into the APDU traffic due to our SIM tunneling, we can also inspect this traffic, and we've analyzed it and found that 2 SIM cards actually were covertly sending binary SMS messages to the operator. This is kind of spooky because it totally happens in the background and the user doesn't notice. So it's like a command and control traffic. And in some cases, even this SMS was billed. Of course, we also had other showcases, so internet measurements. The actual motivation to build this platform was to do some billing-related measurements, some zero rating measurements. And in our paper, we also show that knowing these metrics that are used for zero rating, an attacker could basically gain free internet and do some free riding attacks. Additionally, there is a separate paper on zero rating. It's called Zero Rating One Big Mess, so maybe you are interested in this as well. And with this slide, I want to conclude the presentation. I've put the link to the GitHub because the project is fully open source. So if you're interested, you might want to check it out. Thanks.